In this second video of chapter 2, we start with just briefly discussing the periodic table, and then we are going to talk about the more concept and the calculations that are involved in the mole. Usually you see this picture in classes. In most of the science classes, you see a picture like this one. That is a periodic table. So and this periodic table contains what we call elements or atoms that we know exist on Earth or in the world. So we are just going to briefly discuss how this table is made. But first, we are going to define an element. So what is an element? An element is actually a substance made up of only one type of atoms. So substance made up of only one type of atoms. So an element can be one atom, two atom, or more. That is, an element can be one atom, two atoms, or more. We are going to still call it an element. For example, you can see this element is made up of single atoms. It is still an element. This element is made up of two atoms. Also an element. What matters is, are the atoms of the same kind? If the atoms are different, then it's no longer an element, it's a substance. But the atoms must be of the same type. So, for example, here we see neon is an element made up of a single atom. So neon and xenon are elements made up of a single atom. Oxygen is oxygen, nitrogen are elements made up of two atoms. Sulfur here is an element made up of 8 atoms. But if we look at oxygen here, we see we have an oxygen which is written as this, an element made up of 2 atoms, and oxygen which is written as this, an element made up of a single atom. Both of these are elements. So an atom can have an element made up of several atoms, also can have an element made up of a single atom. So what we are saying is each single atom is an element. But also when the atoms combine and they are the same atoms, they also form an element. Like we see here, single atom of oxygen is an element of oxygen. The combined atoms of oxygen are also an element of oxygen. Elements that have 2 atoms are known as diatomic elements. So for example, oxygen, nitrogen, and chlorine here are diatomic elements. And the periodic table has 7 of these diatomic elements. So that include oxygen, nitrogen, chlorine. Uh, Here I have fluorine, bromine, iodine. Um, yeah, the seventh one, which is hydrogen. So the periodic table has these 7 diatomic elements. The common elements that we meet, that we are going to use a lot in this class, aluminum. So those are symbols. So you can see how the elements are given and their symbols. Chlorine, fluorine, helium, copper, iron, lead. So these are the elements. You can see here, these names are the Latin names of these elements. So you expect iron to have a symbol IR, but that's not the case. We use ferrum, which is the Latin name of iron. The same thing with lead here. Instead of having Le, we have Pb because we are taking it from plumbum. That's the Latin name for lead. So these are the names and symbols of some of the important elements that you are going to deal with. Now, what about the periodic table? The periodic table itself is made up of what we call periods and groups. So, in simple terms, when we talk about the periodic table, it is just a table that arranges elements in the order of increasing atomic numbers. And similarities in the number of outer shell electrons. So because of that, a periodic table has what we call groups, which are vertical columns. So if you are going down, you are dealing with a group. So we can say in terms of groups, if I may get rid of this definition, in terms of the groups, going down here, we have group 1, group 2, group 3, group 4, 5, 6, 7, 8. So vertical columns are known as groups. And then we have periods. Periods are horizontal rows. So this is period 1, period 2, period 3, 4, 5, 6, 7, 8. So a periodic table has vertical columns, which we call groups, and horizontal rows, which we call periods. So it is a periodic table because each each row each row is a cycle, or each period is a cycle. So what does it cycle? The periodic table cycles the outer shell electrons, or it cycles the number of outer shell electrons. For example, period 1 has a single outer shell electron. Period 2 has 2 outer shell electrons, all the way to period 8, which has 8 outer shell electrons. After 8 outer shell electrons, we start all over. Not period, but group. I'm saying group 1 has a single outer shell electron. Group 2 has 2 outer shell electrons, all the way to group 8, which has 8 outer shell electrons. When we go to second period, we have the same thing. Group 1, single outer shell electron. Group 2, 2 outer shell electrons, all the way to group 8. We go to third period, we have the same thing. So we really cycle the outer shell electrons, and therefore we cycle the chemical properties of the elements on the periodic table. Because usually outer shell electrons are related to the chemical properties of each element on the periodic table. So the periodic table has several categories. Group 1 elements are referred to as alkali metals. So usually, because when we dissolve them in water, they make alkaline or basic solution. Group 2 elements are similar to group 1, but we call them alkaline earth metals. They are similar. The only difference is that in group 1, you dissolve metals to form alkaline solution. In group 2, you dissolve metal oxides to form alkaline solution. So here you dissolve like MgO, while here you dissolve like sodium, the metal itself. In between here, we have transitional metals. So, I mean, we call them transition because they are moving us from, if you look at this one, this is 1A, 2A, all the way here to 3A, 4A, 5A to 8A. In between here, we have the B's, 3B all the way to 2B here. So we transition between the 1A and 2A all the way to 3A, 4A, 5A up to the end. So the metals in between, they are transitioning between these two blocks of A. So this is usually an S, we call it an S block. This part is a P block. So the transition metals transition between S and P blocks That's usually where the name came from. But also, as we'll see later, um, transitional metals are a D block, and we'll talk about that uh, in a later chapter. Group 7, Group 7A is known as halogens, and Group 8A is known as inert elements, or we call it uh, noble gases. The reason we call them noble gases is because they like to remain single. They are inert. They don't combine with other elements. So it's a they don't combine with other elements. Why do they not combine with other elements? Because they are inert. In other words, they have filled outer shells. They have filled outer shells. So they are the noble gases. So you just need to remember these important groups. And also on the periodic table, you can see that all the way to here, we have metals. And this side, we have non-metals. So in general, what I want you to find out is if you have your periodic table, you need to show me, if I give you an element, what group is that element? For example, if we take an element here, which is sodium. So sodium is in group 1. So sodium is in group 1, but it's in period 2. We take another element, let me take the element oxygen here. So oxygen is in group 6, or we say 6A, but it's also in period 2. So what I'll be looking for is, tell me the group number for this, tell me the period number for this. This element is above this element is below this element. Now what is the formula for group 1 elements? So you say group 1 elements are alkali metals. Group 2 elements are alkaline earth. Group 7 are halogens. Groups 8 are noble gases. Why are group 8 called noble gases? They don't combine with others. They are like kings, or they have filled outer shell electrons. So that's how you navigate through the periodic table. Now we move on to the calculations that we do in chemistry by defining the mole. Like, what is the mole? So usually the standard that we use for the mole is carbon, like carbon 12. So you take 12 grams of carbon 12, the isotope of carbon 12. If you take 12 grams of carbon-12, you have 1 mole of substances. Now, 12 grams of carbon-12 has 6.022 times 10 to the 23 particles of carbon-12. Now, this value here, this number, is known as the Avogadro's number. So we can say that 1 mole is equal to 12 grams of carbon-12, which is equal to 6.022 times 10, 23 atoms of carbon-12, and which is equal to the Avogadro's number. So this one here is the Avogadro's number. So when we talk about the mole, there are important terms that we need to know. The molar mass. The molar mass is mass of 1 mole of a substance. This mass is different from the atomic mass. Atomic mass is mass of a single atom. So atomic mass is given in the units of atomic mass units, while the molar mass is given in the units of grams per mole, because 1 mole is a lot. So for this class, the symbol for molar mass is MAR. Then we have number of particles. Number of particles of a substance are given a symbol N, big N. So number of particles, the symbol big N. Then we have Avogadro's number. The symbol is Na. The A stands for Avogadro's. So Avogadro's number is just the number of particles, but it is a specific number, which is 6.022 times 10 to the 23. While the number of particles, N, can be any number. For example, maybe it can be 3.1 times 10 to the 23, or 8.5 times 10 to the 24. So N can be any number of particles, while Na is just the number of particles which is equal to the Avogadro's number. Then we have a small m. A small m stands for mass of particles. So mass can be any mass of a substance. For example, for carbon, we can have a mass of 2 grams, a mass of 5 grams, a mass of 7 grams. And the difference between mass and molar mass. For carbon, molar mass is always 12 grams. That is for carbon-12. So this is the molar mass here, while these ones are just masses. So this one has a big M, AR. These ones have a small mass. So 3 symbols that we are going to use. MAR standing for molar mass, N standing for number of particles, Na standing for Avogadro's number, and M standing for just mass. That is 4 symbols that we are going to use. Now, In terms of more, we have three important more calculations, and each of them is going to have a conversion factor. So three important more calculations with a conversion factor. Um, so the calculations are: you may be given a mole to find the molar mass. So you can be given a mole. We have several moles of something. Find the molar mass. So the conversion factor for that is 1 mole is equal to molar mass. Usually the molar mass will be a number or a value. Then you have another conversion. You are given a mole and you want to find the number of particles. So for that, the conversion factor is 1 mole is equal to number of particles. And you have a third conversion. You are given number of particles to determine mass. In that case, you are going to combine the two conversion factors. 1 mole is equal to number of particles. And then 1 mole is equal to molar mass. So take note of these conversion. When I give you moles to find mass, that's the conversion factor you use. Mole to find number of particles, that's the second conversion factor you use. Number of particles to find mass, or I give you mass to find number of particles. You need to use these two conversion factors. So that's one way we solve more calculation problems, and I think that's what we are going to focus on when solving these problems. Another way is to use a pyramid like this one. So this stands for number of particles. This stands for Avogadro's number. This symbol here stands for the mole. So N is number of moles, big N number of particles, NA Avogadro's number. So you can draw a pyramid like this one. So in this pyramid, if you want to find the number of particles, you put your hand here. Like hide this one. If you hide N, if you hide big N, you have N times NA. So it tells you that number of particles here is equal to the mole times the Avogadro's number. That is if you hide big N. Now, if you hide small n, that is number of moles, you are determining number of moles. So number of moles is equal to number of particles divided by the Avogadro's number. So this is shown here. Number of moles is number of particles divided by the Avogadro's number. So that's the second formula you can use. Now the Avogadro's number is always given. You always know it, so you don't need to calculate it. So let's look at problems that we can solve using the information that we have just discussed. Example 1. The number of moles present in 8.25 times 1022 particles of neon is. How do you solve this problem? So this problem, we are moving from, we are given particles and we want to find moles. So which conversion factor do we use? The conversion factor we use, 1 mole is equal to 6.02 times 10 to the power 23 particles. So this is the conversion factor we use. Now, to solve this problem, start with what you are given. So we are given 8.25 times 10, 22 particles. Let me put particles here. That's what we are given. So you start with what you are given and then multiply and then draw a line. So if you have particles here, you also need to have particles this side. So that's what you have. And then once you have particles this side, you come back to this conversion factor. You say, what do the particles go with? The particles go with 6.02 times 10, 23. If you have particles here, it means you need to have more up here. What does the more go with? The more goes with 1. So it's just the starting quantity times the conversion factor that you have. Our answer here, 0.137 more. So this answer is to 3 significant figures because we are starting with a number that has 3 significant figures. So just know what conversion you are using. You are using particles to moles. Your conversion factor is 1 mole is equal to 6.02 times 10 to the power 23 particles, because that is the conversion that contain both the mole and the particles. And your answer will be to 3 significant figures. So I'll erase this and solve the next problem on this same slide. So now we are solving problem number 2. The number of particles in 1.14 mole of H atoms is. So here we are moving from moles to particles. So since we have moles and particles, our conversion factor is 1 mole is 6.02 times 10 to the power 23 particles. But what is our starting quantity? Our starting quantity is 1.14 mole. So you start 1.14 mole. And then multiplication sign. You draw your line here. Since you have more here, you also need to have more this side. So if you have more this side, it means you have particles up here. The more goes with 1 the particles go with 6.02 times 10 to the 23. And to three significant figures, our answer is 6.86 times 10 to the 23 particles. So that's how we solve the mole to particles or particles to mole problems. There is also another pyramid that we can use. Now, if you are moving between mass, number of moles, and molar mass. So N stands for number of moles, as we showed last time. Mass is the given mass. MAR is the molar mass. So these are the formulas that you can use, that you need to learn how to use. Or you can just use the conversion factors as we already indicated. For this problem, we are going to use, at least one of the problems, we are going to use one of the formulas, especially this one. So let's go on and look at more problems. 0.712 moles of a molecule has a mass of 25.24 grams. The molar mass of the compound is. So for this problem, we can go back and take this formula. So molar mass is given by the mass divided by the number of moles. Now this is really simple. You just take your mass here, 25.24 grams divided by the number of moles, which is 0.712 mole. And for this calculation, your molar mass is 35.5 grams per mole. So our calculations is to three significant figures because that's where we are starting. So really, it's just a matter of simply using the formula. Molar mass is equal to the mass, the given mass, over the number of moles. So the second problem here, let me get rid of this. So I am solving the second problem. What is the number of atoms present in 13.5 grams of chlorine? So the molar mass of chlorine, is the MAR of chlorine is 35.45 grams per mole. So here, solving this problem, we are moving from number of atoms. Number of atoms is the same as number of particles. Between number of atoms to mass. So because of that, we have two conversion factors. The first conversion factor, 1 mole is equal to molar mass. So the molar mass is this, 35.45 grams. So 35.45 grams. So that's the first conversion factor. The second conversion factor is 1 mole is equal to 6.02 times 10^23. So here, instead of particles, we'll say atoms. So particles can mean atoms, molecules, ions, and the like. So we have our two conversion factors. But our question here says, what is the number of atoms present in 13.5 grams? This is our starting quantity. So we are going to start with 13.5 grams. That's what we start with. And we know that we have two conversion factors. So you need to multiply here, put a line for the first conversion factor, multiply again, put another line for the second conversion factor. Now here we have grams here, up here, grams, which means we need to have grams down here. So this gram is this gram. So this gram goes with mole. This gram here goes with a mole here in their conversion. Now you have this mole up here. It means you need to have a mole down here because they need to cancel each other, which is this mole. So this mole here goes with atoms up here. So you are going to have atoms. And usually what you are finding is the last one because we are finding the number of atoms. So we just take the gram goes with 35.45. The mole up here goes with 1. The mole down here goes with 1. And the number of atoms is 6.02 times 10^23 atoms. So for this one, the answer is 2.29 times 10 to the power 23 atoms. So remember, if you are moving from atoms to mass, you need to have two conversion factors. The same thing if you are moving from mass to atoms, you need to have also two conversion factors. So let me go on to try to move from mass to atoms by looking at this problem, or from atoms to mass. What is the mass of 2.85 times 10^24 atoms of aluminum? So this is the molar mass of aluminum, 26.98 grams. So for a problem like this one, you also have two conversion factors. So the first conversion factor is 1 mole is equal to the molar mass, which is 26.98 grams. Also 1 mole is equal to the Avogadro's number, 6.02 times 10 to the power 23 atoms. So here I'm putting atoms instead of particles because the question states that we have atoms. Now, from this question, this is our given. This is our starting quantity. So I am starting with 2.85 times 10, 24 atoms. So I know that I have two conversion factors. So I'll put the first conversion factor here and the second conversion factor here. Since I have atoms here, I also need to have atoms here so that the atoms will cancel. These atoms go with mole. So I'll have a mole here. And since I have a mole here, I also need to have a mole here so that the moles cancel. And this mole, which is this one, it goes with the grams. So I'll put the grams here. And since we are finding mass, we are finding this mass, our last conversion should be the grams. And then I'll just put the numbers. 6.02 times 10 to the power 23. And then 1. Here, 1. And then 26.98. So for this problem, to three significant figures, our mass is 128 grams. That's how we solve this problem. So the last part, you can be given a problem like this one, which has more mass, this number of particles or this number of particles. So for this problem, you can practice it and solve it. Make sure that when you are submitting your video assignment, you have an answer for this problem. Just make sure that you practice these problems, and if you have any questions when we meet in class, you should ask those questions. Thank you.